Hello, everyone. Welcome to the first user day for the Otter project. Otter stands for Unified Transcription and Translation for Extended Reality. I'm happy to be here. My name is Vlad Nicolae. I am an assistant professor at the University of Amsterdam. And I'm happy to be here to give you a welcome and introduction to our project today. The schedule that we have for you is going to start after my introduction with two technical demos from José Sousa and Laurent Bessassier, followed by some research paper presentations from Nuno Miguel Guerrero and Marceli Zanon Boito. And then after a brief break, we'll have an exciting panel for you today about multimodal large language models, extended reality models, and the future of NLP research. The panel is moderated by Andre Martins. And finally, don't leave, because at the end of the program, I will be back to walk you through our exciting funding call announcement that we are working on that will be out in the next month. This is an FSTP call from the Otter project for Cascade financial support for third parties. So these times are all UTC +1. So please make note of them and make sure not to miss the part of today's presentation that you are most excited about. First, before telling you about Otter, let me tell you about extended reality itself. This is a bit of an umbrella term that means many things, but the core gist of it is it has to do with immersive technology that enhances our interaction with reality, enhances our senses by adding digital information. Extended reality is a core part of European Union's strategy for our digital future. So for that reason, they're funding a lot of projects to develop technologies in this direction. Extended reality is close and overlapping with computer-mediated communication. This is the focus of the Otter project. It is increasingly common in today's reality, just like we are talking today remotely, possibly not even at the same time if you're watching the video afterwards. We communicate right now through this computer-mediated interface that is to an extent quite rich with audio, visual information, slides, and so on, chat interface. But of course, it can be even richer, and it will definitely become richer and smarter in the coming years. Computer-mediated communication, of course, beyond being a core reality of our day-to-day work lives and personal lives right now, has a huge societal impact. Computer-mediated tools correctly built and built with the right priorities can increase accessibility, can lower carbon footprint, reducing travel, and enabling seamless interaction that otherwise we might have to take long trips to be able to have. At the same time, they have also an important business impact because you can be more productive with the right tools. You can collaborate more effectively with the right tools. Yeah, so extended reality is quite important for us. This direction of research and of technology development has, of course, great potential, especially given recent advances in AI, large language models, and so on that you're probably very familiar with. Of course, these also come with great risks and challenges that we in the Otter project study. So the Otter project develops machine learning research on extended reality models, so multimodal large language models, towards our two driving use cases. The first use case is the meeting assistant use case. This is a speech-first conversation data stream, much like what we're having right now, which can be enriched in numerous ways and summarized and cut and diced in the ways that participants want in order to empower them. And then the customer support application has to do with text-first conversation, but in a large multilingual regime in order to empower people seeking support and people offering support through this computer-mediated channel. The challenges that I just mentioned have to do with the challenges of today's very exciting, otherwise large language model technologies, which I would say they are by and large not XR ready. It is not an established term, but let me tell you what I mean. They are mostly text only, or if not, at least text first, whereas we deal with other means of linguistic communication that is not text speaking right now. They are English-centric, typically. There are models trained on internet data that comes from other languages, but usually English resources dominate and other languages have poorer coverage or are more of an afterthought. Controllability, biases, reproduction of toxicity, and risk of leaking private information are widespread among today's models. There are ways to nudge them or instruct them or encourage them to do things, but no real way to like configure or control in a way that truly prevents undesired behavior. Models, again, by and large, are not open or reproducible. There are, of course, exceptions to this, but the scale and the applicability widely vary. They are, in a sense, brittle. They lack robustness in the sense of often failing with high confidence, failing in ways that they are not able to detect. Sometimes their users are not able to detect. So in some ways, they are not really safe to use in high-risk applications. They sometimes lack interpretability or like any kind of accountability of the decisions or answers being generated. And of course, they are not particularly energy efficient right now. So all of these are research direction targeted by the Otter project in order to bring the technology of large pre-trained models to more confident, reliable, multimodal, multilingual, extended reality-ready models. The Otter team consists of partners from this list of exciting universities and industry organizations. I'm from the University of Amsterdam. Our partners, our organizers today are from Unbabel. And we will have interventions from colleagues from Naval Labs Europe, the University of Edinburgh, and the Instituto de Telecomunicações. Yeah. This is the Otter Consortium. And let me also tell you where you come in, dear audience. Of course, any research project would be moot without adoption, application, and extension. And I'm hoping that you would be the ones to do this. The research that we perform in Otter, and the models that we develop, and the prototypes that we will present to you today are ripe for application extension. And in fact, you can apply to be funded to do such work through our mechanism for financial support for third parties. This is a cascade mechanism for funding short projects. There will be a teaser from me later today. The call will be out in about a month. So after that overview, let's take a step back and look at the schedule again. I was quick, so in about 5 minutes, we can slide into the demo session with Jose taking over from that big room that you see over there. So the demo session will be half an hour, and be prepared after that for the exciting research paper session. After the break, once again, we have the panel, and then I will be back here. Well, I'll be here throughout, but I will be speaking again to talk to you about the funding call once again. So in the meantime, while Jose sets up, I'm happy to try to clarify if you have any questions about what I was just talking about. Thanks, everyone.
Hi, Vlad. Can I start sharing?
Do I need to stop for that?
Let me try.
Go ahead.
Just a minute. Right. I will start by playing the prototype that Naver did with a video that Laurent recorded. And then I move on to the customer service assistant. Okay, you can see this. So we're still a bit ahead of time. Shall we just start, do you think? Or I think we can start, right? Okay. So without further ado, I'll just give the word to Laurent, who is here, maybe not physically, but he left his message recorded. I'll just play for you. Oh, of course, there are technical problems because we have video. No. Just let me figure out the volume here. Share computer sound. No.
Brief overview of the first prototypes of the meeting. Hello everyone, I'm Laurent Besacier from Never Labs Europe, and I'm going to give you a brief overview of the first prototypes of the meeting assistant that was done during the Utter European project. So this demonstration was prepared with the help of my colleague Jos Rosen as well. Let's start with an overview. In this meeting assistant, we really wanted to go beyond the use of an automatic speech recognition system that transcribes the meeting, cascaded with some sort of summarization system in order to get summary of the meeting. Of course, we provide these features as a meeting assistant that is demonstrated here, but we wanted to go beyond. We wanted a smart assistant with which we could basically chat in order to get information of a meeting. Imagine a smart assistant which attended the meeting on your behalf, and you want to chat with it about a meeting you did not attend, or you want to seek information about a former meeting you attended but you just don't remember some aspects. For this, we started by a data collection. So basically, we recorded our internal Utter meetings, and we transcribed them with some off-the-shelf tool called Tactic, which gives us some transcripts with time codes and also with identity of the person we took due to Zoom. These were Zoom meetings mostly. So let's have a look at the demo. Let's load some automatic transcripts that were obtained for a 1-hour meeting we had during Utter. Those transcripts are noisy, but there are some time codes, they have some informations, and for instance here you have a full meeting of 1 hour that corresponds, that goes into the context window of a large language model that can cover 16K context window. Obviously, we can ask a summary of this meeting in English or French for the moment, but you can also ask a shorter summary, like the too long don't read usual lines you would like to know about the meeting to remember what it was about, and you can have this in French as well. But what is the most interesting feature in this prototype is the ability to talk with the assistant about the meeting. For instance, ask who was there, and you will get the answer by the system. And for instance, you may want to know a specific aspect of the meeting. For instance, what did Laurent say about the meeting? So it will be like a summarization dedicated to a specific person who attended the meeting. But sometimes the factualness is not so great. So you need to interact more about the meeting assistant to know what's going on. And as you have seen, we allow the possibility for the user to use a thumb up or thumb down in order to annotate the data. So while interacting with the meeting assistant, we also collect some interesting logs that could be used for further improvement of the large language model or further fine-tuning or instruction of the large language model we are using in this assistant. So here I ask about the few action points that were discussed, and maybe I want to know more about one of them. So this is really a way to dig really deeper into some aspects of the meeting without going to read the full minutes, which are quite long. So for instance, I asking more about the action point number 2 here. And I would get this answer, and then I can again dig even deeper into the specific action points. So I can dig deeper and see when some specific thing was said. And sometimes I need to retry because, as I said already, there are some factualness issues with the assistant. So I can try to know exactly at which time, for instance, some discussion related to the work package 2 were involved. And so I can find the time code and then go back to the transcript and look at what's happening at this time code. But it seems here that the large language model is not perfect on that aspect. Factualness was bad as well, so I'm going to annotate this. It's interesting data for further fine-tuning or analyzing of the large language model performance for that. And so now I'm asking more details about what particular person who I know is in charge of work package 2 and when did she talk about it. And so now I can have this information and see when it was, and now it tells me, okay, it's at the 40 minutes of the meetings. I can dig into the assistant part related to the minutes, and then I find the information I was looking for. And I annotate this as a good answer. So we log all those interactions, so in the form of a JSON file. And it's interesting because from that, we not only keep track of all the interactions, but also we have this annotation with thumb up, thumb down. So for instance, to the answer, what did Laurent say? The answer was considered as not correct, so I will have this -1 here, telling me that this part of the answer was actually not accurate. And I have some other answers that were annotated as good. For instance, we spoke about WP2, this was Marcelli, and we can continue digging into the logs this way and use those logs to do instruction fine-tuning or fine-tuning of the large language model used for dialogue here. So thank you very much for your attention. This was a demo prototype of Otter. Have a good day.
Okay. I'm not sure if there are questions and if someone can answer them, but any questions about this? Right. Let me move to the other prototype. Just let me find the window. I'll also need to open. Okay, this is going to be a bit challenging because I need to type sometimes for this demo. No, it's okay. Right. Okay, moving on then. I just have a small presentation for starting talking about this. I'll start right away. This is the customer service assistant. This is the other use case that we have in Utter, as Vlad mentioned in the beginning. So this is a multilingual conversational platform for human agents with AI assistants. The code, the front end that you're going to see, the prototype that you're going to see is the result of work of several people that are not here. I'm just here to present. So it's Catarina, Bruno, Mathieu, Miguel, João, Luis, Beatriz, and Vera. Okay, getting right to the actual architecture of the system, or at least the sketch of it. In a high level, the customer service assistant is supposed to help agents of customer service to do their job better. And the idea is to enable them to do their job better by using AI. And the way that this AI take form is by using machine translation, by using something called quality estimation, conversational quality estimation, that is going to tell whether the conversation is going through a good end for the customer, so that the agent, the person that is serving the customer, is aware about their emotions, with also the help of emotion tracking, but also with the help of the machine translation. Here we are talking about a use case in which the customer speaks one language and the agent speaks another. So let's say the user is speaking Portuguese and the agent is speaking English, and the system is helping both understand each other, but ultimately the objective is to enhance the experience for the agent. And this has different languages targeted. For now, the languages of the consortium are Dutch, English, French, German, Korean, Portuguese, that reflect all the languages of the partners in the project, the consortium. And let me now show you what is this prototype about in terms of the demo. Right, just a minute. Okay, so here you have our first prototype, in which we have a chat box in which a customer can speak with an agent. Right now, here is the role of the agent. So let's say the agent is an English-speaking person, and it wants to serve this person that came asking for a request, asking for help. So I'll just have to do this thing with the microphone because I need to type. So the agent initiates the conversation, and it wants to greet and ask for help, ask for what's the request of the person. And here is the first feature that we have, that is, as we are going from English to Korean, in Asian languages, and also specifically in Korean, we have a certain way that we need to address people. And mainly when it's in a more formal environment, or an environment in which we don't know the person. And we have here a classifier that is actually telling us, okay, the way that this is written is not really a cultural fit, and you might want to do something about it. And here we have this button generate that is actually going to help the agent generate an answer, or rephrase this answer, this question to the customer. And here it goes. So yes, it's much more formal. Greetings, esteemed customer. In what way may I assist you today? And then we send this for translation to Korean. And there you go. Here's the translation. Here you also have an idea of the quality of the translation. This is given by a Comet score, which is a quality estimation system, a machine translation quality estimation system that we have. Yeah, it gives an idea to the agent about the quality of this translation. Now, I don't speak Korean, but I want to simulate as if I am the customer. So I'm going to use the help of Google Translate for that. Just a minute. Oops, let me translate this. Just get this thing here. Back here, right. So let me just paste. And then now what this, so imagine that this is the customer replying to the agent. And now what the system is going to do is just translating the message to the agent. And actually, it seems to be a good translation. Okay, let me reply to that. And again, so the system, okay, now the system is indicating that the message is okay. And we can just send for translation, which is an automatic translation, and the user is going to receive that. Now, this is for Korean, and this is the overall, is illustrating different modules that we have. During the course of the project, we are going to develop models that are going to be hopefully improving on this. And they can be machine translation models, they can be sentiment analysis models. That is not reflected here for now. There is the Comet score or Kiwi messages and so on. Also, another thing to show is that we have all the other languages here. We can also, speak to the customer or to the agent in these two languages, English, Portuguese, English, Dutch, and so on. And I think that's it for now. I don't know if there are any questions. This was kind of fast, both of them. So one important thing that was not reflected there is just the sentiment analysis. We had it, but for some reason I couldn't show here. But we also have, like when I was showing here, let me just go back. We have a first prototype of that, but it's not capturing here. But basically, when we had the message of the customer, we can also have an idea about the emotion that the customer is having. So if he's frustrated, angry, and so on, or if he's neutral or happy with it. So this is also an important thing for this project. And as I mentioned in the beginning, is going to be integrated also with the quality estimation moving forward. And also connecting to the FSTP, I think there are plenty of interesting challenges and features that can be models that can fuel both use cases, as also Laurent mentioned in the video. So I hope that you stay with us until the end to hear more about this opportunity. Okay.
Thank you, Jose. Are there any questions for Jose? Either speak up or let us know in chat if yes. And otherwise, I would suggest, since we have 15 minutes before the paper session, well, 14 minutes now, perhaps to take a unplanned break and start the paper session on time.
Sounds good.
15 minutes break, right?
So we will reconvene then at, well, my time will be 3:15, 2:15 UTC +1.
Okay.
And we will have Nuno and Marcelli for research paper sessions.
Okay.
I will put up my my slide in the meantime.
Okay. Thanks.
Hello and welcome back. It is time for the research session. We are here for the Otter first user day, and we have Nuno Guerrero next. Are you there, Nuno?
Can you hear me, Vlad?
Yes. Hello.
Yeah. Hello. Okay. So can you see the presentation?
Yes.
Yeah.
Looks good.
Okay. Perfect.
Recording
okay.
still ongoing? Yes. Okay.
I think so, right? Yeah. Okay. So I'm very happy to be here presenting some of the recent work that we have been doing on understanding and safeguarding translation models against hallucinations. So language models, they can hallucinate in very hard to predict ways. And what we mean by this is that language models may sometimes produce text that bears minimal or no relation at all with the input data, irrespective of its fluency. And in particular, this may have a big impact in the task of machine translation because it can easily lead users to misinterpret the original meaning and intent of the source text, especially because users do not understand the source text. So users may mistake the fluency for adequacy when they do not understand the source text. It may cause harm in very unexpected ways. So, for example, case in point is the arrest of a Palestinian man due to an hallucination by a Facebook system in 2017. And it's also often overlooked when assessing performance because hallucinations are so rare that they may not significantly change corpus level metrics, although they do have dramatic impacts then if the models are to be used in publicly or in the wild. So we did, I would say, a trilogy of works on hallucinations, and we started with the work looking for a needle in a haystack. And in this work, we wanted to step away from procedures that had been used in previous works, which studied hallucinations in amplified settings. So basically, because hallucinations are rare, previous work had studied artificial settings in which they may introduce perturbations in the source sentences, for example, misspelling of words or addition of tokens, or even injecting noise in the training data by, say, for example, mismatching references with sources. And these works have contributed with several interesting findings, for example, on the impact of noise in the training data, on the relationship between hallucinations and memorization, on the impact of domain shift, and actually on all other important patterns between, for example, model-based features like attention or even source sentence influence. But there is demand for research in hallucinations that are generated in a clean and natural scenario. So we start by releasing an annotated data set with natural hallucinations in German to English, which at the time of our research was the first data set of natural hallucinations. We also defined a taxonomy that was fit for purpose. Are you having display issues regarding the slides?
Yes, every time that you change the slides, it takes a very long time for the next one to be displayed correctly. There's like a lot of squares that do not refresh.
Oh, I see. That's not ideal. I'll stop sharing and try to share again.
Yeah, sorry.
No, that's okay. What about now?
Yes, it's still the same. All the slides mixed together. You have a lot of squares from different.
Oh.
Well.
Yeah.
I think you're seeing your comments in the slides somehow. I don't know why, but.
Okay. Let me try again. PDF loses animations. I mean, we can lose the animations, but let me see. I can try to share again. Okay. Let's try. Okay, I suppose you're seeing like PowerPoint, and now maybe it's working.
Oh, it's
yes.
great. It's good.
Yeah. Okay. Okay. Great. So maybe you were seeing the notes or something like that. So okay. Well, I'll resume from this point onwards. Then just repeat this slide. So the idea of our first work was that most works that have been developed on hallucinations before had studied artificial settings, because hallucinations are so rare that they try to basically break the model in order for it to hallucinate more. And this was usually done by introducing perturbations either in the test data or by injection of noise in the training data. But and while these works have contributed with findings on the impact of noise, on the relationship between hallucinations and memorization, on the impact of domain shift, and even on the relationship between hallucinations and attention patterns and source sentence influence, we posed that there was demand for research in a clean, natural scenario where you train your models on clean data and you test them on clean data as well. So we started that work by annotated the data set with these natural hallucinations, which at the time of our research was the first one of its kind. And we also defined a taxonomy that was fit for purpose. So we defined oscillatory hallucinations and detached hallucinations. So oscillatory hallucinations are examples in which the model repeats n-grams or phrases in an oscillatory way. And there's also detached hallucinations in which the model actually produces a fluent translation, but that is detached from the content of the source. Now, after having released this data set, we could do some analysis on detection of hallucinations. And we found that, for example, previous rule-based heuristics, which targeted specifically, for example, copies of references in the training data that may be repeated for different unique source sentences, or even proxies to find oscillatory hallucinations via comparison of n-gram frequency, those didn't actually work very well in preventive settings. But quite surprisingly, we also figured that quality estimation systems fail to appropriately penalize hallucinations and do not capture this phenomena very well. In terms of model-based features, we were able to discern that hallucinations may be unstable, in the sense that if you use, for example, dropout at test time and generate a bunch of hypotheses, these hypotheses are very dissimilar between among them, especially when so this is a sign that the model is not confident when performing or generating an hallucination. We also found that relying on low source attention mass may not necessarily work, especially if you only use, for example, aggregated features like last layer attention. And surprisingly as well, we were able to find that sequence log probability, which is so simple, so efficient, works surprisingly well and very on par with, say, reference-based COMET, which from a practical standpoint could not be used in an online or on-the-fly detection scenario. Then we wanted to understand exactly why some methods worked and others did not. So for example, here I'm showing you a plot in which you can see the percentage of hallucinations of each type that were detected by each of the detectors or the filters that we are using. And we see now why COMET-QE fails. It fails mostly to detect the fully detached hallucinations. So hallucinations that are fluent, may be semantically similar, but do not have relationship with the input text. But it does very well with repetition. So for example, COMET-QE penalizes very well repetitions of text. Now, in terms of the model-based detectors, we saw that attention methods, even sequence log probability, they do very well with these fully detached hallucinations, for which COMET does not work as well, but do not deal so well with oscillatory. So there's a bit of a there's no one-fits-all solution in what comes to detection. Then after having detected these hallucinations, we wanted to understand how we could possibly mitigate them on the fly. And we proposed the de-hallucinator. So this pipeline is super simple. We started by checking a translation with a detector. And if it is flagged, we generated several hypotheses using MC dropout. And then we picked the highest scoring hypothesis in the spirit of a re-ranking approach. And the idea here is that leveraging the idea of that hallucinations may be unstable. So among that set of hypotheses, there may actually be a correct translation. And in fact, there is. So most hallucinations can be reversed to correct translations just by activating dropout at test time. Now, this is interesting because it means that hallucinations may not necessarily be related with the deep model defect, but may just be the outcome of some bad luck during the generation process. And also, while most, for example, oscillatory and strongly detached hallucinations are easy to reverse, fully detached ones are not so simple. And this is because there's a big relationship between memorization of the training data and fully detached hallucinations. Okay, and after doing this work and figuring out the sort of approaches for detection, we wanted to see if we could actually improve them, especially in an unsupervised way. And that's the work that we're going to present at ACL next week. This is work done with Pierre Colombe and André. Here, our idea was that hallucinations are anomalous in light of a reference distribution of healthy translations. So by definition, these translations contain content that is detached from the source. So they may exhibit cross-attention patterns that are statistically different from other healthy translations. So the idea is that we propose an optimal transport formulation. We use the Wasserstein distance to compute the cost of transforming an attention distribution of a test translation into those found in good quality translations. So intuitively, this Wasserstein distance measures how the cost of transporting or transforming one distribution into another. And the idea here is that hallucinated translations are more costly to transfer to a good quality translation pattern than those of other healthy translations. So after our approach relies on leveraging the source attention mass distribution, so the proportion of total incoming mass coming to each source token. And here we use an aggregated attention map over averaged over all heads of the last decoder layer. And we build a simple baseline in which we compare to the uniform distribution. So in the context of this problem, it would mean that all the source tokens were equally attended. We also compare to a data-driven approach where we compare the test source mass distribution against a reference set of distributions from good quality translations, and also a simple combination of these two methods. So diving a bit more into the VAS2 data, so comparing the two reference distributions. So the idea is simple. We compute the source attention mass distribution. We then construct a reference set built via an held out distribution data store. And then we compute the Wasserstein distance to all these reference distributions. And ideally, we want to leverage the idea that an hallucination will be very far from all the distributions in that reference set. So we compute a bottom K distance because the minimum would be too noisy. Now, in terms of scores, here I'm showing you the area under the curve. So ideally, a perfect detector would have 100, so it would be able to distinguish very well between non-hallucinations and hallucinations. 50 would be a random score. We see that VAS Combo performs on par with state-of-the-art QE systems like Comet QE. So this is a different updated version of Comet QE that actually has seen hallucinations during training. And we also see that VAS Combo actually manages to outperform previous model-based detectors like the sequence log probability. In terms of the actual types of hallucinations, we saw the same trend with Comet QE being not as good at detecting fully detached hallucinations as other model-based or even sentence similarity models like LabZ. But in terms of oscillatory hallucinations, that's where our method sort of got huge improvements over previous model-based detectors. But we're still lagging behind, let's say, Comet QE, which actually manages very well to penalize these errors. Now, All these works have been done on small transformer models, around less than 100 million parameters. But now we have all these large multilingual translation models, and this is work that that we did in collaboration with people at Edinburgh, and also Pierre and André. Shout out to Duarte as well. And so the idea here is asking, so what about these massively multilingual translation models and large language models? So as I said, previous studies focused on small transformer models, and usually though they were trained on English-centric high resource translation directions, such as German to English or English to Chinese. So there was demand again for research on hallucinations in multilingual scenarios, including lower resource languages. And we departed then from previous studies and analyzed the vast set of multilingual translation models. So here we used a family of massively multilingual NMT models, the M2M family of models, and Small 100, which is actually developed by Naver Labs. It's a distilled M2M large. And we also used the family of large language models. So we used ChatGPT and GPT-4. So in terms of evaluating the models under perturbation, so when we actually introduce perturbations in the test data in order to amplify hallucinations, we saw that, as expected, average hallucination rates generally decrease with increasing resource levels. So models are more prone to hallucinate in lower resource settings, which is expected. We also, quite surprisingly, we figured that distilled models can actually hallucinate less than considerably bigger models, even actually the teacher model. And these may be due to modeling choices or even training data choices, because, for example, Small 100 was trained with uniform sampling across all languages, whereas these massively multilingual models tend to oversample the high resource languages. In what comes to the types of hallucinations, we discovered that large language models hallucinate in very different ways compared to conventional NMT models. So usually hallucinations come in the format of failed attempts to translate or off-target translation. So for example, I think in the paper we mentioned two examples, like this is a Vietnamese sentence, so there is no way, or this is an English sentence, so there is no way we can translate into Vietnamese, or sorry, my language model cannot translate to Russian. So these failed attempts to translate, these were different types of hallucinations that we would never face with conventional NMT models. We also wanted to provide insights on what comes to the natural hallucinations. And we again realized that hallucination rates for low resource languages are very damning. So they can be over 10% for some low resource language pairs. And they're especially frequent out of English than into English, with rates increasing up to 5 times more when translating out of English. Now, we knew that about quality in general. So usually NMT models or models in general, translation models can perform translation with better quality when translating out of English. Then when translating into English, then out of English. We also found the same trend with hallucinations. And we wanted to investigate exactly why. So we wanted to assess the source contribution when translating to low resource languages and when translating out of English. And what we saw is that when translating out of English, models can tend to have less source contribution. So models tend to rely more on the decoder when translating in English models tend to rely less on the source when translating out of English than when they're translating into English. We also realized that when translating to low resource languages, models also have more propensity to detach from the source content. Now here, I'm also showing you 2 models. So a 12 billion model, the M2M large, and the 300 million model, the Small 100. And we see that Small 100 relies way more on the source than M2M large, with values of very close to 0.75, whereas M2M large around 0.4, 0.3. And this is basically because Small 100 uses a shallow decoder. So the decoder only, we hypothesize that because Small 100 uses a shallow decoder, so only a three layer decoder, that it has to rely more on the complex representations of the encoder, whereas M2M large, which is way bigger, has a way bigger decoder, can detach more from the source. We also found that when translations are detached, they may come in the form of toxic text. And this toxic text is actually can be traced back directly to the training data. So you can actually find those hallucinations or that generated text in the training data of these models, which basically highlights how important it is to properly filter your data before training the models, and how important it also is to have the data publicly available so that we can do this sort of analysis. Finally, we also wanted to investigate the mitigation of hallucinations, but now in this massively multilingual setup. And we found that the detached hallucinations are very sticky across models of the same family. So when models are trained with the same training data, even if you scale up, it's very hard to reverse hallucinations that are detached from the source. But you don't have that issue with oscillatory hallucinations, which are way easier to reverse. Now, if you do use a diverse model, so a model that is trained on a different architecture, say a large language model, or even an NMT model that is trained differently with different training data, you can actually reverse most of the hallucinations and eliminate some pathologies altogether. In fact, in terms of what comes to the translation quality, it can be increased dramatically by using diverse models as fallback systems. So we can get improvements of over 25 comment points up to 30 comment points when using a diverse model to reverse hallucinations from another model. So the main highlight is that scaling up to a same family model as a strategy to reverse hallucinations is not effective at all. You should instead fall back to a diverse model that was trained differently. So to basically provide a summary of the contribution, so we contributed in terms of the detection part because we made available a new data set. We provided comprehensive analysis of previous detectors and proposed new ones. On understanding as well, we studied hallucinations in bilingual, multilingual models in a vast range of scenarios. And in what comes to mitigation, we proposed the de-hallucinator and also studied a scenario in which we use fallback systems for when an original model hallucinates. Now, I'm very happy that the work that we have done has been picked up by other groups and has inspired further publications. And more these days, we see more and more work on hallucinations. So just to give you some ideas of what's next, some interesting directions for future research. So one is understanding the contribution of different context components to translations with large language models, because now these models generate translations. They can leverage examples of the task, and they also have to leverage a prompt, an instruction to translate, but we do not know exactly how these large language models balance this information. So it's interesting to explore questions like, how do they use this context? If the role of this context will change when you specialize these models for translation, and in terms of hallucination specifically, if they are still associated with low source contribution, or if now that these models have to leverage very different types of context information, if a low source contribution is not as strong a proxy as it was for NMT models. Also, an interesting direction is to build quality estimation systems that can actually appropriately penalize these errors. We saw that Comet Kiwi fails in comparison to, say, LabZ, which is a smaller model, and it's a similarity model, so it's not used for quality assessments. And LabZ is trained with a translation matching objective, That is very much aligned with hallucination detection because LabZ is trained with a contrastive loss. So it receives a batch of translations, one true translation, and the others in the batch are random translations, and it's trained to specifically differentiate between the true translation and the negative translations. So interesting questions are if we can actually build negative examples that could be leveraged by QE systems to increase robustness and generalization, and also if we can add these properties to QE systems while keeping state-of-the-art correlations. So some strategies could be using back translation as lossy compression, or even explicitly changing the model state by provoking over-reliance or detachment. And that's all I had to say. So thank you very much for attending, and I'm ready, available for questions. Thank you.
Thank you very much, Nuno. If anybody in the audience would like to ask Nuno a question, please speak up or please type it in the chat and I will read it.
I have a question. Well, that's a lot. Thanks. Very nice. My question was actually just clarification. So the model-based ones are really Glassbox. I need to have access to the systems, right? So you cannot apply that to ChatGPT or GPT-4.
Yeah, you cannot. Yeah.
Right. And I'm very curious about LabZ doing so well. Like, you think it's really because of the contrastive loss, or is there more to that?
No, so LabZ is trained with a mix of objectives, but I do think that contrastive loss is very aligned with hallucination detection in the sense that LabZ is trained from scratch to differentiate between a true translation and negative translations. And hallucinations, when they're detached from the source, they actually look like translations that are not respective to that source sentence, but other source sentence. So in that sense, they can look like random translations in a way, especially when they're fully detached. So that's why I think LabZ does so well in this sort of task, which is also very similar to, say, parallel corpus filtering in a way.
Yeah, I was going to mention, I guess one of the state-of-the-art approaches are using LabZ or something like that for filtering.
Yeah, Laser, for example, also works decently, not as well as LabZ, but I think it's the same sort of nature in the sense of that similarity task.
Yeah, that's pretty cool. I had more questions, but
I can ask one first and then you can go back. No, I wanted to ask about, I wanted to ask about the source contribution part of your work. You said you used the empty plus or something like that for that. Can you talk a bit about whether you found this to be like a reliable metric? Is this what you'd recommend to use for this sort of study going further? Because I know that this sort of attribution methods for deep models are they don't always agree with each other, right? So I was curious what your experience was about this.
Yeah, this is a great question. Let me see if I can find. I think I had some slides, or maybe I cannot find them anymore. I don't know if I can find them anymore, but then I can send you. But basically, we use AltiPlus. So AltiPlus is sort of so if you've heard of layer relevance propagation methods in which they try to get a global contribution instead of just very localized attention patterns from a specific layer or specific head, Layer actually considers the whole transformer model and uses the concept of attention rollout to sort of get a global contribution. Now I found AltiPlus to work very, very well for hallucinations. It's incredibly, I found it incredibly reliable. And when using with human data, it actually has, for example, for fully detached hallucination, it has like an area under the curve of nearly 98 or 99. So it's really very good. So when it comes to these very sort of detached, examples, AltiPlus works really well. Now, if we are trying to discern between good translations, I'm not sure because I haven't studied that, but AltiPlus is not like the concept of faithfulness is also a bit faulty, right? But as far as I can understand, like as far as I've tried different contribution methods, Altiplus work the best. And I think it's mostly because it does provide you with a global contribution, and it provides not only a contribution from the source, but also from the previously generated tokens. So I can send you some pointers if you're interested in that.
That's very helpful. Thank you. Yeah, I'll reach out offline.
Yeah.
Thanks. Who has the next question?
I had another one which is just related to this source part. Can you just remind me how do you assess that? I missed that part.
Sure. So we use Altiplus. I'll try to be. Altiplus is a method for estimating global contributions. Okay. So I'll try to make it very, very brief. So Altiplus will estimate a matrix of contributions, which you can think of as a matrix that will, for each generated token, will measure the contribution of the previously generated tokens in the target and also the source tokens for generating that specific that specific token. In fact, it's not necessarily for generating, but it's for the mixing of the contextual information. So that representation was influenced by which tokens in the context. And we get a source contribution by, for each source token, we measure the source contribution of that token, the total source contribution, and then we average across all the target sequence.
Okay. Thanks.
Yeah.
All right, thanks. Thanks, Nuno. Thanks, Jose.
Thanks.
Does anybody else have any last questions for Nuno about his great presentation? If not, we have Marceli next. Hi, Marceli. Welcome.
Hello. I'm going to share my screen. Okay, are you able to see my presentation and to hear me?
I am.
Okay.
So I assume if I am, everybody else is.
Okay, I cannot see the chat, so if there is something, please let me know.
Will do.
So hello, everybody. My name is Marceli, and I'm here to present Naver Labs Europe's winning submission to the EWSLT 2023 low resource track. For those that are not familiar, EWSLT is this conference that have yearly speech translation challenges. This conference is organized in several different tracks. So this one is about the low resource and dialect track. And for each track, there are a couple of language pairs, and then researchers can submit their systems for each language pair inside of each track. So let's start about talking a bit generally about how do we do speech translation nowadays. The classical setting for speech translation would be the one above, in which you build what is called a cascaded speech translation system. Just to remind you, a speech translation system is a system that receives as input speech utterances, and then this system should be able to produce translations in the target language. So a cascaded system will accomplish this by interfacing the translation procedure by NEASAR. So the system will first produce a transcription to the speech signal, and then working from this transcription, this model will, this approach can apply a different model in order to transform transcription into translation. And this is cascaded speech translation. But more recently, a new paradigm has gained some more traction, and it's the direct speech translation approach, in which we are gonna directly translate speech into translations without having this intermediate step. This does not mean that you cannot produce transcription at the same time. There are approaches that do that, and this is still considered direct speech translation. The difference here is that when you're producing your translation, you have the speech in your as a context. You still have access to the information in the speech. Whereas for cascaded, when you're producing translation, you only have access to the transcription. So there is some degree of error propagation. So why are we interested in direct speech translation? As I mentioned, we have no error propagation because we are working directly from the speech signal. So we have all the context that we need to disambiguate some things that could get lost in the transcription. Another reason could be oral and unwritten languages that are actually most of the existing languages that do not have a standard transcript. So for these languages, you cannot write it down. And then you do not have the data to build a system that will first transcribe and then translate. Finally, imagine that you are on the meeting a system use case from Utter. You have online meetings and you want to have simultaneous translation going on. Having a system that first transcribes and then translates, this is extra latency, and this will make the process slower. So these are not all of them, but some reasons why direct speech translation is interesting. And in this work, since I mentioned this was our submission to the low resource track from WCT, we are mainly focusing on oral and unwritten languages and in building a direct speech translation system that works for them. So let me give you a context of last year, EWCT 2022. In that year, a new language pair was introduced for the low resource and dialect track. This language pair is the Tamashek French language pair. Tamashek is a language spoken in many African countries, between them Niger and Mali. And this language pair, this data that was shared with the community was 17 hours of speech in Tamashek with aligned translations in French with no transcripts because Tamashek doesn't have a standard transcript. And then you can see in this table the submissions from that year. And if you look at the blue scores, you can notice that these are very, very low. Actually, the best submission for that year is scored only 5.7 blue. And we, of course, cannot compare directly blue scores from one language pair to another. But at the same year, the systems that were running on the high resource, the offline track for the WCT, these systems were starting at 25 blue. They were going over almost 40. So this is a very huge gap between direct speech translation systems that are being employed in high resource settings and the ones that were being tested for low resource settings. So why do we have such a gap? This gap happens, in your opinion, because nowadays direct speech translation models that rely, of course, on a pre-trained speech representation model that serves as a speech encoder. This is very beneficial for building a better representation from speech. And then what is usually done is that some sort of decoder is plugged, is interfaced to this pre-trained model, and then this is fine-tuned end-to-end for the speech translation task. The problem here is that if you try to do something like that for Tamashek, which is what the winning submission from that year did, they had a pre-trained model that was trained on a lot of Tamashek raw audio, so they were able to build a somehow good speech representation for Tamashek. But then when fine-tuning, they only have 17 hours of aligned speech translation data, and this data had noise, had code switching, and then this decoder that was very cold and not able to produce fluent French translations. This, in your opinion, made the approach not very performant. So we decided to participate this year and hopefully boost the scores for the Tamashek French from last year. And at the same time, we were also interested in participating on the Quechua Spanish language pair from the same track, because this was a very challenging setting in which the organizers only gave us around 2 hours of aligned speech in Quechua and translation in Spanish, and plus around 50 hours of Quechua transcriptions, Quechua speech plus transcriptions that we could leverage. And that was all the data that we had for building our speech translation systems. So what we decided to do is to build one single system, build something that was multilingual in order to have more data for this speech translation fine-tuning. We were also interested in working on top of existing pre-trained models in order to build something that is parameter efficient. And another challenge that we put on ourselves was that we wanted to build something that would be useful for this task, would be useful for speech translation, but that could still be useful when doing text-to-text translation. So this is the architecture that we came up with. The idea is that if you look at the left corner, we see some Quechua speech that is being fed into a pre-trained speech representation model. This model is not fine-tuned, it's just a regular pre-trained model that we use as a feature extractor. And then once we have these speech features, we are gonna reduce their sequence length by training a couple of CNN layers. And then the output representation, we are gonna feed it into a pre-trained multilingual machine translation model. So this pre-trained multilingual machine translation model, it can be something like NLLB, or MBART50, can be any text-to-text pre-trained model that is multilingual. Then what we did was to replace the first end layers with a small n. We explored between 2 or 4 layers. We replaced the first encoder layers of this pre-trained model by what we call modality-specific layers. Basically, we make a copy of the pre-trained weights that we had, and we keep this so that we can still leverage text. And in parallel with a copy of these layers, we fine-tune them for being able to project the speech representation into this text-to-text model. After these modality-specific layers, then for each encoder or decoder layer of this architecture, what we do is to add a low dimensionality adapter in each one of them in order to adapt to representation. And then with this architecture, we are able to, following the speech that is, following the path that starts with the Quechua speech, we can go from Quechua to Spanish. And by keeping the text layers on the bottom, we can still go from Quechua text, for instance, to Spanish. So we are still able to hopefully perform both at the same time, speech and text translation. And then this solution is parameter efficient because the only things that we are training are the small dimensionality adapters that are shown in yellow, the few encoder layers that are fine-tuned, they are shown in orange, and the CNN layers, there are again very few that are shown in red and are trained from scratch. For training this architecture, we then we take advantage of existing pre-trained models for speech. We use some the ones that were released last year that were dedicated for Damashek, but we also experienced with some general purpose multilingual models, such as the multilingual Wave2X. And for the pre-trained neural machine translation model, the text-to-text port, we experiment with NLLB and MBART50, finding that the former is more performant at the same weight size. And then for the data that we use for fine-tuning, we have the low resource speech data that I mentioned, the 17 hours of Damashek. It's actually 15, the rest is validation and test. 2 hours of Quechua, Spanish, and the 50 hours of Quechua ASR. And then in order to make it work, we found that it was very helpful to add, to make this a more multilingual setting and add more languages to the mix. So we added a lot of many hours on high resource languages that had an interesting target. For us, an interesting target is a language pair that shares the target language with one of our low resource languages. So for instance, we want to translate Tamashek into French. So other language pairs that translate a given language into French, these are helpful to have at our mix because this allows our decoder to be better fluent in French or the Spanish. So after adding all of this data and we fine-tuned the model, and then we reached state-of-the-art results. We built one multilingual model with all this data that is able to reach first place for both the Tamashek French language pair and the Quechua Spanish one. For Tamashek here, we see the progression of scores from IWSRT 2022 to 2023. We see that we started at 5.7 last year. There was a post-evaluation submission at 13, and our submission pushed the scores up to 20.7 blue, which is a very nice increase. For Quechua, having only those 2 hours of aligned translations that I mentioned, we are able to achieve 17 blue, which is also a very good score. And then the advantage of this model that we proposed is that this model is not only good for the low resource languages that it covers, but it can also be very competitive in high resources. So what we did was to train our multilingual models that produce Quechua and Tamashek translations. We trained them on the MTED-X languages from a previous challenge, the 2021 one for the high resource track, which is called the offline track. And we compared our submission against the winner of that year, which is the FAIR submission. And we see that for the same training directions, we are able to beat this submission. And for zero-shot directions, we are very competitive, with the difference that for us, the language pairs that are on the zero-shot condition, these are real zero-shot language pairs. And for this submission, these were only domain zero-shot, which means this system saw these language pairs, but with other data sets. In our case, it's really zero shots. And even so, we are able to get results that are almost tied with theirs. And we do all of this by having 6 times less trainable parameters, which means that our approach is quite efficient. Finally, one more interesting characteristics of this multimodal, multilingual model that we propose for translation is that we noticed that we're able to perform cross-modality domain transfer, which basically means domain adaptation for text-to-text translation, but using speech-to-text translation data. So if we ignore the speech path of our model, what we did was to evaluate our scores on MTED-X text-to-text translation without using the adapters, and then by using these adapters that were included for the speech translation. And what we see is that by using these somehow speech adapters for text-to-text translation, we are able to boost our average scores on 2.7 blue. And this will, of course, always be less than adding new adapters and fine-tuning them on the same data set, which would give you 5 blue in average. But it is still very interesting to notice that we are able to transfer domain knowledge when training on cross-modality. So basically, in summary, we built this multimodal and multilingual model that is able to perform speech and text translation. We adopted a parameter-efficient training strategy by leveraging existing pre-training models and training only interface and a couple of adapters. We are able to achieve state-of-the-art performance in low-resource speech translation for Tamashek and Quechua, and very competitive results in high-resource settings with this very flexible model. And the next thing that we want to do is to make sure that we are also scoring the ASR, which for the moment is leveraged, but is still not optimized. and then extend this model to other speech tasks and text tasks. And that's it for me. Thank you very much.
Thank you, Marceli. It's very nice. Congratulations on the very good performance. Oops, my video was not on. We have time to take questions, right? Please, anybody who has any questions for Marceli, let us know. In the meantime, I have a question. I was very interested in the modality specific and like cross modality, the learning stuff that you mentioned, because
yes.
I think a common experience is that this sort of multitask learning is very hard to get it to not degrade, right? Like to not forget the other or like the original input. So do you have any like tips or advice or things that you observed there? Like maybe freezing things, I don't know, like if you just can revisit this a bit more.
I think that this approach was successful because it successfully projected the speech representation into the text space, so that by fine-tuning the adapters, these adapters end up being helpful for the text itself as well. So I think that's one reason why it works. Another thing that I didn't show, but that we also tried in the paper, and it was kind of fun, is that we also evaluated translating low resource languages to other languages that were seen during fine-tuning or not seen at all. So for instance, we translated Tamashek into English, which was seen on the pre-training from the text-to-text model and on the fine-tuning, but also into Korean, which we didn't train with, and we were still able to leverage the information that was on the pre-training machine translation model. And this is, of course, because the architecture is frozen and we are just adapting on top of that. So yes, freezing the architecture is a big part of it.
I have a follow-up question.
Yes.
So following up on this question about the multimodality or cross-modality, like in Otter, this is very important, right? So for doing that, do you think we need some sort of parallel kind of modality data, or it can be like some data in text that is not exactly parallel with the other modalities? How do we envisage that? If you have an idea, I don't know.
Do you mean for building a system that can do both speech translation and text translation in the context of Flutter?
Yeah, or what you say here about domain transfer or something like that. Yeah, let's say what you said.
In this setting, I can answer for both. I think in this setting, we had this pre-trained model that for text, which was trained on Chrome data, I guess, for NLLB. You have a lot of Chrome data. So this was not adapted to the MTED-X domain, which are like these talks. It was not that bad, of course, because it had a lot of data trained with, but it was not that domain specific. And by having speech data on that domain, you're able to use the same adapters and adapt it for text. So based on this, my intuition is that we do not need to have perfectly aligned domain data for both text and speech data. And we can instead leverage the other modality as a sort of supervision for performing this domain transfer. So for instance, if you want a good text-to-text machine translation model that works on meeting settings, maybe we could fine-tune on speech data from meeting settings, and then we could leverage this knowledge for text-to-text.
Okay, thanks. I had another question, if nobody has, which is related to something that you said right in the beginning about fast decoding.
Yes.
I guess, yeah, the point of the presentation was not really about that, but I was just curious, what exactly do you mean by fast decoding, and how this materializes in this kind of application? You know, what kind of changes?
Here what I meant to say was just that if you build a cascaded system, you need to have an online ASR. That this is quite okay, because since there is no reordering for an ASR, you can get online solutions that are very good. They are already deployed on Zooms and other meeting technologies, for instance. But then not only you need to decide where do you stop to start feeding it into your translation model, but you also have the error propagation. It's just that doing it in a cascaded fashion for meetings, it's complicated. I'm not sure. I do not think it's what it's done, for instance, for the online translation of meeting assistants that exist today. I would bet they are direct approaches because of this interfacing, which can be quite costly in time, simply because you have to transcribe and then you have to transmit it to the translation that's going to translate.
Okay, got it. Thank you.
Thank you. Any other questions for Marceli? If nobody has any questions, I suggest we can take the break early. So
20 minutes break instead of 15 minutes break.
Indeed. Let me show you all the schedule again. So this is where we are right now. The next event on our calendar is going to be the panel, which starts at 3:30 UTC +1. So that is from now in 19 minutes. I will see you all in 18 minutes and 30 seconds.
See you. Thank you.
See you. Thank you.
Thanks again to Nuno and Marceli for their great presentations. Hello and welcome back. We are here for the Otter User Day. Hope you had a nice break. Up next, we have our panel, which is hosted and moderated by Andre. So Andre, would you like to take it from here?
Okay, so I think we're still waiting for one of the panel members, but I'm going to start sharing my screen. Okay, do you have Julien here?
Yes, he's here now.
Okay, perfect. Okay, so it's a great pleasure to have this panel here. The topic of the panel is multimodal large language models and the future of NLP research. And I'm very glad to have a very good set of speakers. So I'm going to start by introducing the speakers, and then they will start their interventions, and then there's going to be a couple of rounds of questions. So let me start by introducing Lexi Birch. Lexi is a reader in natural language processing at the University of Edinburgh. She's also the co-founder of Aveny.ai, a startup in speech analytics and conversational AI. And her main research is on machine translation and multilingual dialogue. Thanks a lot, Lexi, for accepting the invitation to be here. Our second guest panelist is Alina Karakanta from Leiden University. She is an assistant professor at the University of Leiden. She received her PhD in computer science from the University of Trento on the topic of automatic subtitling. This was a collaboration with the machine translation group at FBK. And she works on many topics: neural MT, speech translation, audiovisual translation, and so on. Then we have Carol Scarton. Carol is a senior lecturer at the Department of Computer Science at the University of Sheffield in the UK. Before she was academic fellow at Sheffield, where she did her PhD. And her research interests include online content verification, personalized NLP, text simplification, machine translation, and document level evaluation. She's also the secretary for the European Association for Machine Translation and its international counterparts. And finally, last but not least, we have Julien Launay from Hugging Face. Julien is leading the extreme scale team at Hugging Face, where he's working on pushing the boundaries of open source models and tooling. And before that, he was a PhD student at École Normale Supérieure in Paris-Saclay, and he has been part of the Falcon Large Language Model Initiative. Okay, I hope I got everything right. So without further ado, we're going to have a first round of initial interventions. So let me propose that we start with Lexi, first on the list. Lexi, are you ready to share your screen?
Lovely to be here. Thank you very much for the introduction. I'm going to share my screen. The topic for the debate today was on interesting applications for multimodal language models and the future of research in large language models. So I thought I would take this opportunity to talk about ongoing research that we're doing here at the University of Edinburgh with PhD student Radina Dobrova, which I find particularly interesting. The task is audio descriptions. And so the reason why I really like audio descriptions is that there's a really good motivation for them. So what are they? They're widely used for accessibility. So if you're a very large content producer, like say the BBC, you'll have certain obligations for making your content accessible to a wide range of audience members. So the BBC, in fact, has to contract humans to produce audio descriptions for up to 15% of all of the content that they produce. So there's an entire industry producing audio descriptions for their content. That means that it's not some sort of undefined abstract task. It means that there's a really good motivation for it and a really good way of describing how to do the task well. You know, so other tasks that are maybe multimodal are much harder to define and could be done in one of 100 different ways, which makes it very hard to do a good job in producing it automatically. It also makes the task very hard to evaluate. So that's why I think audio description is a really cool task. There's also not a lot of work been done on it so far. So generally what happens is that it's it could be an extremely multimodal task. What you've got is you've got some video, a sequence of stills from a video. So you have a lot of information from image features and video features, and then you could also have context from previous audio descriptions that have been produced. You might also have dialogue, so you might have text from previously transcribed audio of the dialogue. So I mean, in this particular example, you can see that the target, what we're trying to produce here, could depend upon all of these things. So, you know, it could be as Karen stares gloomily out of the window, a man approaches toying with a lighter. She turns her head and finds Jack standing beside her. You might also have or dialogue, can I buy you a drink? Yes, I'd love one, sit down. And then the target is to produce this final sentence. He takes out the seat, takes the seat opposite, and then places his lighter on the table. So, you know, it's an extremely multimodal task and potentially very, very challenging. You might find that it's in fact not just kind of the immediate context, but it might in fact be knowledge of, you know, the characters from, say, the beginning of the movie or world knowledge that you might need in order to generate these audio descriptions. It's something that we couldn't have done like a year or two ago, I don't think. The level of performance of our models just wouldn't get there. I mean, there has been previous work, but from like 15 years ago on generating audio descriptions. So it's really exciting that we can now have the capability to start trying to tackle tasks like these. But to get to the point about, you know, research and what is the role of research, and you know, why don't we just hand these tasks over to industry? You know, why doesn't Google just develop an audio description tool and make it an API for us all to use? You know, us as researchers, what is our role? So I think it's, you know, there's so many questions regarding a task like this, how to do it well. You know, what is it? What are people doing? What are humans actually trying to achieve when they do audio descriptions? Do they write about the context that they can see and hear, the immediate context, or how far back do you need to go in the movie in order to be able to do generation competently and well? You know, how much is just inferred from general knowledge? How much could something like the script help? So this is from The Devil's Wears Prada. You know, do you need to be able to have the aligned movie script in order to generate the audio description well? You know, do we need to think about this task in terms of, you know, predicate argument structure, and do we need to predict particular verbs? You know, is it good enough to predict the verb remove shades, you know, or is it better to use kind of more colloquial language like she pulls off her designer shades? You know, these kind of questions are really research questions. And so, you know, I'm quite confident that, you know, in order to do these tasks well, we need the time and space that academia provides. You know, we need kind of a couple of years worth of somebody looking at a task deeply, analyzing it, you know, doing experiments with human annotators and human evaluators to try and answer these kinds of questions, research questions. And to be quite frank, I don't think that industry has that kind of time or interest. And also, it does seem like in industry there's been a recent trend towards publishing a lot less and sharing a lot less as these models have moved into more of the core of the business. So I think I'll stop there and let other people speak. Thank you.
All right, thank you very much, Lexi. So next we have Alina.
Hello. Okay, start sharing. Okay, so hello from my side too. So I will also focus a bit on audio description. So today we know that our communication is becoming increasingly multimodal. So we use screens for work, for entertainment, for education. But NLP has had, for a very long time, it has had a very hard time dealing with multimodal problems. So since we have all these technological advancements to date, it's time to ask the question whether multimodal large language models can become a tool towards barrierless access to information and communication. And I'm going to focus on two fields that have long been ignored by NLP research. One is audiovisual translation, so how we can provide access to multimedia products for people speaking different languages. And second, on accessibility, mostly media accessibility. So how do we provide access to multimedia products for persons with sensory and also cognitive impairments? So the first and most well-known type of audiovisual translation is subtitling. Subtitling poses specific problems in the sense it's not just a simple translation of a dialogue, but it is a timed text. This means that it has some duration, and it's also split because we have limited space on screen, it is also split into smaller pieces. So subtitling is a very multimodal problem. It is very much related to speech because the text appearing on screen needs to be synchronized with the speech. Often we also need agreement with the image. For example, if I need to translate the phrase, let's have a toast, it would be translated differently if I hold a glass in my hand or 2 pieces of bread. So information from the visual modality can also give us, is also necessary in order to be able to do this task properly. The second type of audiovisual translation that is very well known is dubbing. In dubbing, the mouth movements of the actor need to be synchronized with the translation. I will give you an example. Here we have the phrase something funny, which if we give this to a machine translation system and we ask it to translate it, it would perfectly well translate it in French as quelque chose de drôle, so something funny, perfectly. But this for dubbing is not enough. It would not ever be credible that the actor has actually spoken this. So in this case, a human dubber would translate this as ça vous fait rire, which matches exactly the phonetics of the source. So for dubbing, having information from the lips, so from the visual modality, it's necessary to perform the task, together with the speech. So knowing exactly when the utterance starts and when the utterance finishes. Now moving to accessibility, we have also subtitles for the deaf and hard of hearing. These are very important and are becoming more and more important because a larger part of the population is losing hearing in the recent years. Here, the difference with subtitles in different languages is that we also need to include information about sounds, sound effects. So man giggling, thunder, crashing, So we need to be able to recognize this also from the audio. Plus, we need to give information about the speaker, who is actually speaking, who is actually saying what. As you can see in the right, we need to have information in order to say this comes from this actor, this comes from the other actor. So again, speech is very important as a modality here. Then moving a bit to visual accessibility, recently this company, Be My Eyes, has used a large language model, so ChatGPT-4, in order to provide a visual assistant for people with blind and low vision people. So apparently this is an app that people can use, and it will be, they claim, the same as having a volunteer reading things out for them. So since large language models are already passing the visual modality, previously we mentioned audio description. I would only like to add that audio description is not simple also as a task, because the description needs to fit between the dialogue. Plus, we need to be very selective in the information we use from the visual modality. So we cannot describe everything. We need to understand what is the most important part of the information to include in this limited space. Another type of audio description is also in culture. So we don't only use audio description for media products, but for example, in museums or in art exhibitions. Again, knowing on what to describe and how to describe it, it's also a very difficult task. Describing a painting is something very different than just describing one simple object on a table. And last, another interesting application is pictograms. So pictograms are all over around us, even if we're not very aware of them. For example, traffic signs are pictograms. Pictograms are a very nice way to pass information to people who don't speak a particular language, to people who cannot read, or also to people with some cognitive impairments. So large language models, multimodal ones, can also be another way to create pictograms, or also to transform information from one modality to the other. So to close, after all these applications where multimodal large language models might be useful, it's time to discuss now if these tools can help us break the communication barriers. And if yes, what is the price that we're willing to pay in terms of privacy and environmental costs?
Okay, thank you. Thank you so much, Alina. So next we can move to Carol.
Hi, just 1 second. Let me share my screen. If I manage. Okay, it's interesting. Just 1 second. Apparently Zoom changed the permissions on. I need to quit and reopen apparently. Sorry about that.
No worries.
Hello, sorry. Can you hear me?
Yes.
Let's try it again. I'm really sorry. All these things sometimes don't work as we want. Can you see my screen?
Yes, that's working now.
Okay, brilliant. Can you still see the screen or? Yeah, there we go. Right, thank you so much for the invitation. I'm going to talk a little bit about our work on misinformation analysis and how my personal opinion on how these multimodal language models can help or how they can actually impact this field of research. So just stating the obvious firstly, so of course we are seeing a breakthrough in technology. Large language models are changing the field. There is no question on that one. I do think prompt engineering is becoming a major challenge. So at least the research that I have been seeing, whenever people change the prompt, just a minor change sometimes impact the results quite significantly, which may become an even bigger challenge if the prompt involves images, text, audio. So this is something for people to start to think about. However, despite these models' impressive results, we still have, issues, and some of them are very naive. So, for example, I just prompt ChatGPT to translate the nurse helped the doctor to Portuguese, and it propagated one of the major bias that is basically translated the nurse to the female version while the doctor translated to a male version. And when I prompted to explain the decisions, for me, the most shocking part is at the end when it basically says that it's a correct and natural way of translating while it's still assuming a gender. And I think this kind of mistakes are still there being propagated, regardless of this being a problem since we have been started working with machine translation and data-driven machine translation. So I do believe that multilingual large language models can bring a great deal of change. So some were already mentioned by Alina and Lexi, like image captioning on demand. That's definitely a major or direct application, in my opinion. We could even use that to disambiguate translation. So if we have an image of a male nurse and a female doctor, then perhaps ChatGPT could translate that correctly. It could even produce art. So if you think about illustrations for books and so on, and there are many, many other applications, in my opinion. But today I want to talk about this misinformation analysis research that we do here in Sheffield, and which would be the impact or that I see with this model. So one major one that I'm really looking forward to try is to use these large language models to see their capabilities of identifying image and videos being used in the wrong context. So here are two examples where the images are real images. So if you pass through a traditional pipeline of identifying whether an image has been tampered and so on, it will become clean because the images are real. There is no tampering on the images. However, they are used out of context to propagate disinformation. So the first one is just people saying that there were protesters storming the White House, but in fact, this picture was taken in Ohio State House. The other one on the right here is a famous one on 4chan, apparently. So every time that there is a mass shoot, this picture circulates, and this guy is just a comedian, an American comedian, and they just claim he is the shooter, and then it becomes another cycle of misinformation being shared. But perhaps if the large language models can query the web and can identify some of these images online, this could be quite helpful. Another direction of research that's quite relevant to misinformation analysis is stance classification. We have been doing that for text for a long time. So the idea is someone posts a claim or a false claim, and then we analyze which is the stance of the replies towards a given claim. And we could do something the same for a video, for example. So imagine there is a video from the NHS about the vaccines, and we want to perceive what people are talking about, whether they are propagating disinformation, or which kind of actions the NHS needs to do to convince people that the vaccines are a good thing. And another interesting thing is these language models can sometimes explain as well some of the decisions. So on the stance, for example, we tested with one of our data sets, and I apologize for some of the language here, but the most interesting part is how the language model could more or less explain why it believes that the classification of the stance of the reply towards the tweet is to query. So that is also a very interesting application, mainly when you think you are informing journalists or other end users. However, this comes with a price, as everything that we do, every technology that we produce, there are two sides to it. So some of the bad things that can be done with this kind of models, I believe, is that malicious actors could then create more credible misinformation. So, misinformation with audio, video, and so on. And that could be disseminated in different ways and for different, targeting different people, which will eventually hide coordination. So it will be more and more difficult to detect whether people are acting together on a malicious intent. Is already super difficult, but just thinking that for this specific group of people, I'm going to share text. For this other specific group of people, I can share an audio. For this other specific group of people, I share videos and so on. It may become the deepfakes 2.0, so may become easier to create deepfakes, or at least to prompt them and make it to become less need of experts to do it, because at the moment most of the deepfakes need to be quite edited and so on. And a final problem that I can see is that this information may become part of those models, become part of their training data. So here's one example of a Google image search where this image was inputted, and the output was, the best guess for the image was an immigrant attacking a nurse in France. But in fact, it's a drunk person. The video is for a drunk person attacking a nurse in France. There is nothing to do with immigrants. But because it was shared so many times by many websites that it was an immigrant, Google then starts believing that it's an immigrant. So that those are the main problems that I see. Thank you for the invitation. I just put the pictures of the people working on many different stuff on the team. And yeah, looking forward to the discussion.
All right, thank you, Carol. We are running a little bit behind time. Now we have Julia, and then we're going to have a few rounds of questions. Julia, when you are ready.
Yep, and I just realized that I did not allow them to share. And give me a second, because it's my new Mac. I think hopefully now you can modify it live. No, I have to quit and reopen, sorry, but I will be fast afterward. Give me a second.
No problem.
Up, and hopefully, yeah, now it's good. I think you can see my screen, and I think if I put it in big, it's better. Yeah, I will be fairly quick. So yeah, so thank you for having me in this panel, and I think the previous speakers have already spoken quite a bit about what's exciting in terms of multimodality and some of the challenges. The point that to me feels very exciting is that multimodality is a really big thing for open source to unlock, I feel. We have seen an explosion essentially in like how many LLMs have become available open source over the past like few months. This is kind of like the birth moment of LLMs, where this kind of capabilities are really spreading, and this means an increase in diversity and capability, which is really great. And kind of the logical question could be what's next, for all of these open models. Partly, I think there is some questions about reinforcement learning, because currently the community is very focused on self-instruct approaches, which I do feel a bit short of reinforcement learning and matching the gap with stuff like Claude or ChatGPT. So the question is obviously the scale of this model is still fairly, like, let's say an order of magnitude or 2 orders of magnitude smaller than what is like GPT-4 or even Palm 2 or that kind of stuff. So here as well, there is some stuff to be done. But to me, a big goal, and that's kind of like the subject of this panel, is like multimodality. And actually, this is a thing where even closed source solutions are just barely aware, like they are aware, but they are not really publicized, like GPT-4. The vision version for alignment reasons and for scalability reasons is not quite yet available to everyone. As Gemini by Google and by Google DeepMind was going to come out at the end of the year, but it's still, like there is not a big solution yet. So I feel there is an opportunity for open source to be perhaps even ahead in some ways. And obviously there are a lot of technical challenges. If you look at Flamingo, which is probably like the leading way to imbue like a LLM with multimodal understanding of images. 1 year afterward, most of the models are only like 80 to 90% of the way, like the open source models. And it's really hard. Like the scaling is difficult. The adaptation dynamics are very complicated. There is increased data needs, like data I/O just on a cluster. It's very annoying. There is also limited downstream instruct data. If you want to do RL on top of this, it is becoming common, or like even self-instruct. There is limited data that is multimodal for this, which is actually quite a big problem. But I think it's also very exciting. And some of the stuff that I find exciting is that regarding specifically images, is that much like text, we can find images in a very scalable manner from web corpora. So it means it's not going to be as hard. Like it means probably like we can have very fast progress once we can make this data good. There is also the capabilities of like emergent capabilities. In the GPT-4 paper, they have this thing where it can do OCR. And this is actually done by like gently training on like screenshots of web page and web page themselves, or rendered LaTeX and LaTeX itself. So this kind of stuff is really cool, and I think could really bring cool capabilities to LLMs. And I think, like personally, from a research perspective, I think it's really interesting also to explore approaches, because currently Flamingo or GPT-4 are like a posteriori adaptation for vision. So you train a text-only model, and afterwards you do a vision adaptation. But I think like one approach that is very exciting is to do this end-to-end from the start. And especially like I think stuff like Party, where you represent images as like tokenized images with a VQGAN. So Party is not quite multimodal, obviously, but this kind of approaches for LLMs would be very exciting. So I think it's a very exciting area where there's a lot to do as well for the community and for open source.
All right, thank you very much, everyone. So let me share my screen again. So now we are going to go through a quick round of questions. I think we have roughly half an hour. So I will start with a quick round, and then we'll open questions from the general audience. Give me just a second. Okay, so let me kickstart with a question which touches Julien's presentation. So you talked a little bit about the challenges in developing native multimodal LLMs and all the challenges that are around it. Do you believe that all the future LLMs are going to be multimodal, if you think like in a window of 2 or 3 years? Or will there still be room for text-only LLMs, or like in some problems we might still prefer modality-specific LLMs? And also, what are the challenges of applying these models in the wild? So, for example, Aline talked about some of the challenges that arise when you want to apply LLMs in the real world. So what is your perspective on that? Maybe I can start with Julien because his presentation is fresh, and then we'll look to the other panel members.
Sure. I think on the perspective of like, will all features LLM be multimodal? I think when we talk about LLMs, like there's actually a few different things we talk about, but like the very, very big, like foundational model, like GPT-4, that kind of stuff that are very large and that are like kind of like the flagships. Yes, I think all of the flagships will become multimodal in the coming years. Now there will still be room for specialized models, smaller specialized models, because I think multimodality is not free. It will come at a cost, you know, in terms of like difficulty of training, scaling the data, scaling the compute, and all of that. So I think this way. I also think, you know, there is a lot of premise of people of like, images will help, you know, models understand text better and that kind of stuff. But for now, it's kind of iffy. Like there is very limited work where you get better scaling, fundamentally better scaling by adding images. It seems like text is like the predominant modality for the model to understand the world somehow. I don't really understand why. Like it's a bit strange, but it seems to be what it is. It's kind of an interesting question if it will stay the same. So yeah, kind of like I think the flagships will become all multimodal, and for the challenges, I will leave it to the other speakers who probably have a much more expertise on this than I do.
Okay, thanks a lot. Alina, do you want to go next and speak a little about the challenges that we see in the audiovisual space?
Yeah. I will mostly focus on LLMs will have the same problems as transformer models and previous approaches. So in speech, of course, performance drops a lot when we have background noise, when we have different accents, which are not represented in the data. Very often gender differences also. So speech recognition, for example, has lower rates for males than for males. And of course, we also have multi-speaker events where we don't know exactly where the source of the sound. But another challenge can also be when the modalities do not agree. Because so far we think that both modalities or all the modalities show towards towards the same object or the same sense. But for example, when we have discordant modalities, think of memes. We have one image showing one thing, but the legend is humoristic, so it means exactly the opposite of what we have. So how do we deal also with these cases? How do we know if modalities agree or not? That can also be another challenge.
All right. Lexi, you talked a little bit about speech translation. This is also something very connected to the other projects. So what do you anticipate as the main challenges in the speech and text world?
I think we still haven't solved the problem of long context. We've come from a couple of decades of translating sentence by sentence, and there's been quite a bit of work doing document level translation just for the text modality. But I think when you're in the speech world, the segmentation into sentences is very unclear, and how much context you need in order to translate correctly is still not entirely solved. I mean, it sounds like a really simple thing to fix, but I think when you add another modality in, I mean, even in text, it's a question how much context to give for prediction. I mean, the more context you can give, the better. But with speech, you can't keep a context of an hour long, and it's probably not going to help you anyway. With video, the same. So probably that's a challenge to resolve, is with the different modalities, how much context and how to segment different contexts. I think is something fundamental that we still need to grapple with.
Okay. Carol, do you have any thoughts about these points?
Yeah, I think the first question, I think one of the major issues that we already have is how expensive it is to deploy such models. So even the only textual-based ones are quite expensive to deploy. So multimodality may still be a problem, at least for universities and for research, small research centers. In terms of challenges, I believe that with the kind of text that we use of the misinformation analysis research, or not only text, but any kind of input, it is very problematic because it is user-generated content, so it can be anything. So I think it's going to be quite challenging, the same way that is for humans to classify a stance, for example, or to decide whether something is misinformation or not. Those models are not going to be magical and solve the problem. We just need to be smart on how we use them.
Mm-hmm. Okay, so I'm going to just select some questions because I don't have a lot of time and I really want to hear questions from the audience. But this one is actually a very important point for us that are in the Ether project and for a lot of other people in the community. So many of the LLMs that are currently available, and this happens very clearly in many of the open models that exist. Many of these LLMs are English-centric. They are trained on a lot more data in English than in other languages, and their performance tends to degrade considerably if you use them in multilingual settings. I would like to discuss a little bit, which solutions we can try to develop for this problem. Julian touched a bit on two approaches in a different context, which is either trying to adapt models that already exist, or trying to develop models that have multiple modalities from scratch. But in this case, we can think about multilinguality. So do you want to comment on that? Maybe we can start with Carol, that was the last one speaking before.
Yeah, sure. I don't know. I mean, for the last question, so how can we really leverage knowledge from other languages to a new one? The answer may be yes, because we have been doing this for a while and it seems to work okay. The question that I always have on this scenario is, okay, what would happen if our focus was completely in devising the best language model for another language, instead of, oh yeah, I'm just going to get whatever parameters, whatever works for English, and I'm going to apply to this new data. So I don't think we will ever know, because we'll never have the same level of data availability for other languages like we have for English. And leveraging knowledge may be the only way to go for smaller, for low resource languages, right? So I think we should at least try to bridge the gap that way. Is the low hanging fruit.
Okay. So who wants to comment next on this one?
I think there's a very interesting research agenda here. Do we adapt the very large models with small amounts of monolingual data from large numbers of other languages? Do we train up a massively multilingual translation model and translate text and use our English large language models? I think it depends on the applications, probably. Are we ever going to get a fantastic general purpose problem solving model in, Yoruba or Marathi? I'm not sure. How low resource, can language, how many languages can we expect our very large language models to support successfully? 10, 100, 1,000? these are all really interesting questions, and I hope that many people in this audience are working on them.
Aline, Julien, do you want to comment on this?
Yeah, sure. I think it's actually a very interesting question. Like, something I had a lot of thoughts in my team over the past few years, actually, especially since we are involved in Bloom, where it's very massive multilinguality is very hard to get right. I feel like it comes at the expense of the English capabilities. Usually, the models. There is one thing that is very clear is that models share very little knowledge across language. They share some, obviously, but it seems that it's somewhat limited. So when you add, you add 10 billion tokens of French to 100 billion tokens of English, or you remove, you remove some of the English to make room for that, well, you lose some capabilities in English, whereas ideally, you would want to share. And this makes, accommodating low resources language and everything difficult. And so, I mean, there is a kind of a solution to this, which is not really a solution, which is just scale, doing that kind of what Palm does or Google does with Bard and Palm 2. If the model is just gigantic, you just put every language, and they might not help each other too much, but they still probably help each other a bit, at least, especially so for the low resource one. And so it kind of works. This is kind of a cop-out. This is not a great solution. This is and it does mean as well that your capabilities in low resources languages will never be as good as they are in English. And actually, interestingly, so take this with a grain of salt, because this is some experiments we did a bit ago, and we didn't go as far as publishing them because it's a line of work we kind of dropped, but we would like to get to at some point. We measure the alignment of the gradients across languages. So you have two batch. You have a batch that is full English, a batch that is full French, for instance, or full Spanish, and you measure, the angle between the updates. And essentially, what we found was that the updates are not quite orthogonal, but they are not very well aligned. And essentially, this probably means that the representation, the word models that are being learned by the LLM, are probably quite disjoint between languages. So it learns multiple times the same context, and it doesn't share that much capacity across languages. And this is only the feeling I think that most people have right now. And you can see it in scaling laws. You can see it if you do this sort of experiments. The big question will be, how do you align, all of this representation so that, one token of English also contribute to one token of Basque, for instance, that kind of thing. I think it's a really big topic that is, I think we will solve. I think it will be solved in the coming year or two. I think it has an architectural solution. I think there is a way to enforce in a transformer this alignment. So I think it will be solved, but it's definitely it's a huge question and could be very, very interesting.
Okay. Aline, do you have any thoughts?
I think the answers covered. Just catching up from the last point, maybe it makes sense to see what elements we can use from large multilingual models to support the lower resource languages. So if we can distill information that helps the performance in low resource languages, or if we can invest in adaptability techniques that can raise the performance for these languages with limited data.
All right. Okay, so let me move on to my last prepared question, and then we can open the floor to the audience. This is switching gears to something different. So Julien mentioned in his presentation, is focused on developing open models. And now there's lots of discussion going on about regulation, the AI Act that is being prepared by the European Commission. What should be the position, in your opinion, of Europe regarding LLMs? There's currently lots of fragmentation. I see multiple groups developing, what they claim to be European LLMs. The current discussion around the AI Act seems to be, penalizing a little bit open source models, in the sense that it requires the same certifications that it requires for everybody else. What are your thoughts about this topic? So Julien, maybe you want to start here?
I think, to me, I kind of have a more distant view on this, which is that kind of whether we like it or not, LLMs are here to stay. I think it's going to be a foundational technology for the future. I think, this works super. they work amazingly well. This is a technology that I think is here to stay. Or if it's not exactly LLMs, you know, if instead of having a transformer, like an attention mechanism, you have a state space model, it's kind of the same idea. From a regulation point of view, it's not going to change much. I think this is here to stay, and I think this will redefine very large part of our economy. So I think it's really, really important that that we do things right, like that governments and that European Union do things right. To me, the best, you know, that can be done. Obviously, there needs to be to watch out, you know, for any potential downside. But I think right now, the harms of large language models, they exist, but they have not caused massive harms in society yet. So I think we are still on the watching out. We are still on the good side. You know, we are not too late to take action, and we should be careful not to take action too early, because we could damage the downside, and the European Union could end up, you know, a bit, I don't want to say once again, but I will say it, once again behind, you know, other actors like the US and everything. So I think it's excessively important to support research in this area and to have like very large, like, and this includes industry research, but obviously academic research. And the good news is that it is very easy to support research in this area. Build massive clusters, and I do mean massive, like I mean clusters with 10 or hundreds of thousands of GPUs. Make them easy to access for researchers, easy to use. Like, you know, every PhD student should be able to access, you know, like 30 A100 or more, you know, like even 100 A100. Every PhD student in Europe should be able to do this in AI. I think it's really important. So it's very easy to do. Build very large clusters, make sure that the researchers are well paid and are well funded so that they can get students, so that they can offer good quality of life to their students, so that the PhD students, you know, are not paid like barely above minimum wage. And that's it. And essentially from a political point of view, I think if you do this, you will succeed and you will get Europe to be a leader in the space. So to me, it's really, really important to support.
All right. Do you have other opinions here?
I think he's absolutely right. I think if we consider the cost of the intervention from the European Parliament in supporting the development of this industry, it's really tiny compared to the cost of supporting other potential industries that are also interesting and important. But because, you know, clusters are expensive to create and maintain, but at this point in time, the potential impact of this research would be so huge that it's really, it seems like a no-brainer. I really like your ideas. Thank you.
Okay. Carol, do you want to say something?
Yeah, I mean, I couldn't back this idea more because it's a brilliant idea. I think it's exactly what should be done. I personally do believe that that's the way, instead of spending energy and efforts trying to regulate something that is difficult to regulate. But it is a hard problem, and I think Europe needs to start thinking that we are already behind what is happening in the US and outside of Europe. So if we want to still keep competitive and not sending our data to stakeholders somewhere else, we need some kind of in-house solution. And that's a brilliant idea, a brilliant way of doing it.
Okay, Alina, do you have anything to add on this topic?
Yeah, so we should also keep in mind that legislation, and in general Europe, parliaments, governments, are moving at a very much slower pace than research. So it's very important to keep the communication with the legislators, researchers and legislators, understand the risks from early on. So the legislation that will be necessary in 3-4 years can already start to be prepared, so to set the foundation. Because if the European Union decides to pass a directive, it means that the states might implement this in 5 years from now, so it will be already late. And another thing is that I think Europe should also invest a lot in dissemination. So we also, as researchers in European institutions, dissemination to the public, plus improve the literacy, AI literacy of our students, of the public, of the users of the large language models. Because I think this is not, they are not aware. Many people use them, and more people will be using them, even being unaware that they are using them. But they will not be aware of the risks and of what is going on behind. So also dissemination and literacy is something that should be put up on the agenda.
Yeah. Okay, so is there any question from the audience? Let me stop sharing my screen. So if you want to ask a question, just raise your hands. Or any question from the panelists to the other panelists?
Hello, I can try to make one. Ah, there is one.
Go ahead. Yeah.
Go on, Barry. Barry's first.
Barry?
Sorry, I'm just going to try and let you see me. Oh, I have to plug in my camera. So, yeah, I hope all the panelists in the audience are familiar with the metaphor of the Babel fish from science fiction. So if you don't know, this is the idea of this is like you have this little fish and you put it in your ear and you can instantly understand
conversations in whatever language.
No. So I'm just wondering, what do you think? I'm assuming that we don't have such a Babel fish just now. You can disagree if you want, that it is buildable. But what do you think the barriers are to building such a thing? And can multimodal LLMs help with these barriers at all? If any of the panel have any views on that? Or should we build such a thing?
What's to answer this? Or you can also pick a panelist, Barry.
Carol is smiling. I'm not sure if that means she thinks it's a silly question or she.
No. I think it's a difficult question. I mean, I don't think anything we have at the moment, even LLMs, are ready to do that kind of job. But they can do something. Like I think it's the same. My analogy would be the way that people use Google Translate. It doesn't solve all the problems, but they still use it. So it could be a very interesting application where people just ask text form and then receives an audio back. And then instead of, even trying to pronounce or to communicate, just play the audio and communicate on a different language, which would be quite interesting. Where multimodality changes the scenario, I think it makes it a bit more complex instead of solving the issue of the bubblefish or creating it. It makes it more complex to actually get it right. So because a lot of these models, when they generate whatever they generate, there is the risk of hallucinations, right? So if you ask something to generate on a video that includes audio, that may become quite a complex challenge. So, but yeah, I think we should definitely try research on that direction, and I think we have been doing somehow, but of course the technology is not there yet, in my opinion.
I think there is a case that, we may have ended in a bit of a local minima on this. Like, I feel we have kind of ended up in a position where translation technology is good enough, but not perfect. Like, if you think about it, the experience, when you're in a foreign country, you pull out like the Google Translate app or whichever is your one of choice. And it can kind of do a bit of audio, it can do a bit of picture where you take a picture and it translates like some of things. It can kind of do a bit of all of that, but not unified and all kind of may. Like, I think, to this, I would genuinely think that at least for big languages, I'm not talking about for low research languages, but I think there is a real research challenge in terms of connecting, like getting good performance in terms of translation on low resource languages. But for the big languages, I don't think there is fundamentally any research problem here. I think it's a product problem. It's a very hard one. It's a very hard engineering and product problem of scaling models and getting them in a nice, UX, where you can nicely merge, like an audio thing, like emulate your voice, nicely take a picture and get the thing. Like, to me, it really feels like this. So this makes me confident that this will be solved by Google or Apple in some version of iOS or Android in the coming years. For big languages, for low resource languages, it's going to take more work on our side and as researchers to bridge the gap. But it really feels this way to me. Like, it feels like there is no fundamental obstacle, and it's more of a product problem. And this is not to diminish it, by the way, because I think very often this kind of like bringing everything together with a nice UX and everything is sometimes harder than the research powering it. So like, it's not to minimize the thing, but it's like, I really think it's on this side more than on the research side.
Okay, any more thoughts on this? If not, Jose also had a question.
Can you hear me?
Yeah.
Yeah, my question actually fits well as a follow-up from the Babelfish question, because I guess all the topics we discussed were like adding capabilities, either multimodality or multilinguality. And this means that we need to scale the models. But for doing something like Babelfish, we cannot use a GPT-4 if we need to put that in a small device in the edge. So what are your thoughts about that in terms of research and in terms of vision for this kind of models? Do you think scaling up all the way and not thinking about that is the way? Do you think there is some way to actually compress? Do we need all the data that GPT-4 or the biggest model that we have use and all the capacity, or is there any way that we can, make this more compressed, let's say? I don't know if we have an answer. Is it?
Yeah, I think this is a really interesting question because it's a lingering one in the field. I would want to say, like, firstly, I think, so there is a few things here, like there's a question of inference, like decoupling inference and training compute. Like, this is by far the biggest challenge right now, is decoupling inference and training compute. So like spending a lot of compute at training to make the model better, but then having very cheap inference. The way that we have been doing this currently is just training for longer, which is a solution, but it's not perfect. The way that people like OpenAI are starting to do this, and also for scalability of the infrastructure, is by using mixture of experts, which is another axis which enables you to do this. But it's a very big challenge to do this. I don't fundamentally believe in like compression or like that. Like for specific tasks, sure, I think you can print the model for a specific task or whatever. But as a generalist agent, I think the parameters are actually here for something, and all of the data on which you train is actually important. I think you can draw down the inference cost by optimizing, the model for inference. And I think we are gaining a lot with hardware. Like if you look, at people running like a 7B or even a 40B, 30B model on their MacBook Pro, like it's pretty impressive. I think like there is a lot more that can be done in exploiting this. But now, to go back to the example of the Babelfish, actually, I don't think Google Translate runs at all locally. Like, I'm pretty sure that the app, you can download some language packs, but I think it doesn't work very well, if I remember right. So, for the Babelfish, I would also be ready to just connect to a data center, with there's 5G everywhere in the world, soon there is going to be like 4G powered by Starlink. So you're going to even have it if you are in the middle of the ocean at nowhere. So I think it's kind of like, like you can offload this sort of stuff in the first step. And then, in 10 years, when the hardware is put up, you can have it locally. It's kind of the way that I would see this. I think the scaling up, like it's very important to keep, like, I do see an importance in keeping models that the community can play with, because I think we can learn a lot from people, a lot of people interacting and everything. But I don't think this is, I think this is a component, and you also need at the same time to be pushing at very, very large scale and to use these learnings to push further. And, a few years down the line, what was very large scale once is going to become like something that many more people can run. It's going to, yeah.
Okay, there is time for one more quick intervention before we finish. Does anyone have any thoughts on this question from Jose, or some other remark that they want to bring?
I think that it's another great opportunity for academia to try to make high performance models that are much smaller than the commercial ones. There's some trade-off on performance, but they generally would be far more useful for research and even for deployment if you're not, part of a large industrial lab. I think there will be a lot of work in this direction, and it's very important work.
Okay, so thank you very much. Thanks to all the panelists. I really enjoyed this panel. And I think now we have a break. And I think we are coming back at 4:45.
No, there is no break.
Oh, there is no break.
There is no break. Don't leave.
Okay, so you are taking it from here, right?
Yes. So there is no break. I just have 10 more minutes to tell you about the FSTP, and that's the end of today. But first, thanks again to the panelists. That was a very interesting discussion. Thanks, everyone. So in keeping with my red arrow tradition, here is where we are now. So I would like to end today's very nice meeting and user day by giving you a small teaser about our financial support for third-party program. This is a component of the Otter project. Because like I said before, while we are doing research and use case prototyping in Otter, we are also here to encourage the growth of the ecosystem. And one way through which we can do this is this Cascade project from the European Union, this Cascade system. So through Otter, we will be able to fund some third-party organizations to further develop extended reality applications. We will open the first call soon, within the next month. But because the user day is happening now, I am able to give you a bit of a teaser with the details which we have more or less converged upon so far. Of course, all of this is preliminary, but you can see an up-to-date version on our website, he-otter.eu. And we have a contact email specifically for this FSTP financial support for third parties program. So the objective of this call will be, so we are looking for projects to develop or pilot applications using XR models, like the ones developed within Otter or others, in new sectors, working towards enabling new types of human-machine interaction and so on. So the XR model, once again, in the EU terminology, we're talking about pre-trained neural networks, like large language models, but with a multimodal twist, adaptable to a large variety of form of expressions, not limited to speech and text, image as well, interaction, language domain, styles, and intent. So here are a few examples of projects that we think would be very interesting to receive submissions about. Improving or demonstrating efficiency, either inference or training, very much like Jose's questions from moments ago. Designing interfaces for using these models, extending XR models to new languages, domains, or modalities, applying them to new tasks, building resources for XR models, studying evaluation of XR models. So the way this project will look like is we'll be able to fund up to 200,000 euro per project. There will be 2 calls. The first call is coming out within a month, and the total budget is around 895,000 euro. This funding scheme is based on lump sum payment. There will be half payment at the start and half on successful completion of the project. And I'm talking about 6 to 9 month projects, so fairly short ones, including a development part and the dissemination part that you will have to describe in the application. Submission will be happening between August and October of this year. There will be a lightweight application and evaluation of the proposals. We're talking about a form of around 5 pages or so, a very structured one. And the projects are expected to start work in December of this year and go on for between 6 to 9 months, depending on the plan that you submit. Eligibility includes small, medium enterprises according to the Horizon Europe classification, and also research organizations. But I'm talking about a single organization per project, so you cannot apply as part of a collaborative consortium or something like that. It's an individual application. And of course, it is limited to countries that can receive Horizon Europe funding. Full details and pointers about this will be in the official documentation once we finalize that. And as I mentioned, there will be a similar call next year with the rest of the budget that is not allocated this year. Resubmission of a revised version of the proposal, if it doesn't make it the first time, is allowed, encouraged, depending on the reviews you will get back. So once again, for more details, once again, all the information that I said today and more is currently already posted on our website in a tentative preliminary version. And the final version will be ready soon, between a few weeks and by the end of the month, when the call is officially open. I hope you are interested and you will join us in developing XR technologies. If you have questions about the FSTP, I could maybe clarify things right now, but also information is not entirely finalized yet. So there will be questions I won't be able to answer. But please feel free to shoot them my way. And in the meantime, as I'm waiting for any questions about the FSTP, I want to take the chance to close today's very exciting user day that we had together. Thank all the speakers, the panelists, and the demo presenters for their efforts in communicating our work in such an exciting way. I had a great time watching everything. I hope so did you. And on that note, I would be happy to close. Thanks again, everybody, for joining, and see you at the next Stutter User Day.
Thanks very much, Vlad.
Thank you.
Thank you.
Bye.